This is Science Max, experiments at large. Science Max!
The container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola, 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this, the Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up. You take a bottle of tap water, attach it, and carbonate it. Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk. It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice, carbonated hot sauce. No, wait, carbonated, that was a hot sauce. No. Carbonated clam chowder. Oh, there you go, carbonation, not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again. Hey, Chris!
Hey, how's it going?
Chris from Logic's Academy. I had a problem with the pumpkin. It kind of got larger than I expected.
It's okay, I think this one's bigger than what we need anyway.
Chris shows me a scale model trebuchet, one we can use to test a few ideas before building our maxed out version.
Go on
and
here.
you've got little mini pumpkins!
I know, don't get too attached.
The first is the arm length, getting the right ratio. That means how long one side of the lever is compared to the other. When talking about a ratio, you write it like this, 1 to 2. It doesn't matter what the actual measurement is, just that this side of the lever is 1 of that measurement and this side is 2, or 2 times longer than this side. And it turns out a 1 to 2 ratio arm wasn't great.
Well, that could be better.
It could be better.
So we tried a 1 to 6 ratio arm. The 1 to 6 arm threw the pumpkin further, but not a lot further.
Better, definitely better.
Better? Then we tried a 1 to 4. Turns out 1 to 4 is the best arm ratio.
Whoa! That's pretty good.
Chris also had an idea about hanging the weights.
Because as you see here, these go straight down. And going straight down actually makes this spin even faster.
So when we do the big one, we should hang the weights off the end and not attach them to the end.
That's right, and that'll give you some extra distance.
Excellent. Let's fire this last one.
Okay, 3, 2, 1.
Whoa!
Pretty good.
Yeah. Okay, I wonder when we make the big one, do you think we can get it through the goalposts?
Oh yeah, I think we can do that.
All right, let's try it. All right.
Based on what we've learned from our small-scale trebuchet, Chris and I made a maxed-out version!
All right.
This, I think, is
Wow.
as big as we could possibly be expected to build this.
This is huge.
We have the length of our arm, which
Right.
is important.
Yes, and we've got to add weight here, so
Yeah.
we're gonna like loop this in. Whoa!
Oh, I guess that's because I took the weight off.
Yeah,
So, the arm is 4 times longer on this side of the lever
right,
than on that side of the lever.
right. So this arm goes 4 times faster than that side,
But
but we're gonna need a lot of weight.
Like our small version, we needed to hang weights on the back of our trebuchet. So I got a rope and put some weights on. But because our new version is so maxed out, we need a lot of weight, which I needed to get on a rope and drag it over.
okay, almost there.
And I needed to lift it onto the arm. I needed to lift it onto the arm. I lift it,
You know, maybe we should do this together.
and
Okay, you take one end.
and we lifted it.
That's gonna be a problem, Phil.
I'm kind of glad that happened because there was no way I was going to be able to lift that.
I know, it was way too heavy, and we need something stronger that can still hold the weight and still give us the hinge that we want at the top.
And once the weight's up there, if the rope broke,
That would be bad news.
that'd be big time bad news. Okay, so we need a new solution for getting the weights on the trebuchet that is not.
Not rope. We need something
Not rope.
stronger and hopefully that still has the hinge on it up here.
Maybe we have some sort of bar system that we could hang.
Yeah, I'm thinking metal.
Yeah, metal, definitely metal.
Definitely metal.
Metal is better than rope
I think so.
for holding a whole bunch of weight. Okay, let's
Okay,
get that done.
Let's do it.
All right, I got some metal over in the shop over here.
Okay.
Chris and I had some trouble getting the weights on our maxed out trebuchet.
That's gonna be a problem, Phil.
So we had to come up with a new system. A metal bar that pivots on the bottom of the lever arm. It's got lots of spots for weights, and we could lift the weights one at a time to attach them all. We start out with
255 pounds. How many kilograms is that?
113.3 continued.
Yeah, that's what I got too. All right, that's definitely enough weight, right?
Definitely.
Okay, let's fire a pumpkin.
Let's do it.
This trebuchet works the same as the other models, but because it's so much larger, we really need to haul on the rope. We attach the arm to a quick release, which allows us to hold it in place until we're ready to fire.
Oh, here we go.
Okay.
3, 2, 1.
Whoa!
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 We launched a bunch of the same size pumpkins and got a pretty good idea of how far we were throwing them.
Oh!
Wow.
Okay, you know what? We should leave this here so that we know how far that last pumpkin went.
And then try to beat it.
And then we try to beat it. We haven't gotten through the goalposts.
It seemed to handle the more weight pretty well. I think we can add even more. What do you think?
I think we should add all of the weight. This
Okay.
is science max. This is not like science minimum.
Let's max it out.
We
maybe.
totally maxed it out. Okay, all the weight.
All
the weight. All the weight. Good morrow to you. I am Lord Fillington IV, and welcome to my medieval castle. My father, Lord Fillington III, had his castle besieged by catapults, and he had to share his prized collection of snow globes. Well, I, Lord Fillington IV, have made a few improvements. First was forgetting about snow globes. Those are so last season. I collect limited edition Science Maximals stuffed toys. And I've collected them all, and I'll never share. Hello? That Lord Fillington has been hogging all the limited edition Science Maximals, and he won't even trade. I mean, look, I've got offers, and all I need is a Fricto. But he won't trade. Surely you can trade.
Never! I have all the Frictos and I'll never trade! Ha 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 ha!
That's it. Time to build it.
Oh, you're gonna build a catapult and knock my castle walls down? Well, I've learned a thing or two from my father. I, too, have catapults. Release!
Fortunately, we've got a new invention of our own. A trebuchet.
Oh, fiddlesticks! They have a duck pate.
Trebuchet.
A what? A Mother's Day? A Hudson's Bay? A Cabernet? I can't hear you. You've got to come closer. Release!
The trebuchet was the best thing around right up until the invention of gunpowder. It could throw farther than anything else, even catapults. What you do, you see, is you put something in there, and then you put a big weight up there, right? And this goes down, that flies around and flies over the castle walls, all from far enough away where he can't get me with his catapults. And it works like this. 3, 2, 1.
No, didn't make it. It's too high. It's too high. Ah! All right, I give up. I'll trade. Oh, that's quite nice. I like that.
Oh, and that's how trebuchets were used in history. Sort of. Our giant trebuchet launched a pumpkin pretty far.
Very cool.
But now it's time to max it out further by adding even more weight. All the weight, all the weight, all the weight. So we increased the weight to 425 pounds. That's a lot of weight. Okay, are we ready?
I think so. I can't wait to see what this thing does.
I can't wait to see how heavy it is to pull. Turns out pulling that much weight using our rope was really tough, even with the mechanical advantage of our lever. There we go. We found another pumpkin of the same size, but then we started having another problem. 3, 2, 1, go!
Whoa! Look at how high it is!
What? Whoa! Go!
Whoa!
What? Whoa! So, I think we're going a little too high.
Yes.
It was almost straight up. How far the pumpkin goes all comes down to when the rope slips off the pin at the end. If the rope slips off too early, the pumpkin goes up and not very far. Too late and the pumpkin goes straight, which means it'd hit the ground sooner and doesn't go as far. A 45-degree angle is just right. And how do you adjust it? By simply bending the pin. 3, 2, 1.
Whoa! That was great. Great.
That went way farther than 60. We should have had another sign.
I don't even know how far that went.
Yeah, there you go. Science Max, experiments at large, trebuchet. So, one of us has to clean up the pumpkins and the other one has to put the trebuchet away.
Right.
Pumpkins! Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Now, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, it's, you know what, you go and I'll meet you.
Make sure you're good.
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this.
Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do we do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job, but it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right, now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think do you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket.
Yeah.
Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so
Let's see.
it went, and it flew, and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in a, at the end of the arm. But
Yeah.
if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it, and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later. Pumpkin drop! Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, Gravity, but I'll beat you next time. I'm gonna get a broom.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big.
The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here.
This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud?
And yes, this is something you should not try at home.
This note makes the glass vibrate the most.
Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks.
The vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science!
Seeing sound vibrations is fun.
This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds.
I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure.
Then, what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water.
I've got some yellow cornstarch and some blue cornstarch.
This experiment works the best with low notes.
I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. And let's try it with books.
The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is.
Right now, it's pretty wide and it's not that tall, so the center of mass might be around here.
But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider.
The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, whoa, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And, ha-ha, a single stack of boxes. Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! 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 This is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube.
If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks.
Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket not by making it bigger, but by making more of them. How many more?
400 caps all glued down, 400 antacid tablets, or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down.
We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on.
Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness!
It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean this
All
up
right.
afterwards.
Yeah,
Okay.
let's do it.
Okay, let it go. Whoa. Whoa. I'm an acid, and I'm a base, and we are enemies. Whoa. Well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons.
You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react.
Whoa. That is until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton? Oh, no, really. I could. Please take it. Oh, well, thank you. That's very generous. Have another. No, perhaps, maybe I will. Here's one. Okay, maybe just one. But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water,
Nothing happens. Oh, water! Water! Come on! What'd you do? What? Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals. Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you can do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. Ha-ha! It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing. Even more amazing when we max it out. This is a steel drum. What we've done is we put some water in it and we're heating it up to boiling so there's nothing but hot air inside the drum. This is an airtight cap, which we use to seal the drum. And now we cool the drum off. Hey, Trevor, give me a hand. Ready? 1, 2, 3, you lift! That's good. This pool is filled with ice. What we're doing now is cooling off the steel drum, which will cool off the air inside it. Which means, eventually, the air inside the steel drum will be a much lower pressure than the air outside the steel drum.
Because this steel drum has a lot more volume than a 2-liter pop bottle, it takes a lot longer for the air to cool down. The other thing to think about is that it's a steel drum. I could stand on it and it wouldn't even dent. But sure enough, after a few minutes... Whoa! Check it out! The barrel has totally crushed. The low pressure air inside the barrel wasn't enough to withstand the force of the regular air pressure that you and I walk through every day. The air pressure all around us is enough to crush a steel drum. How cool is that? Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like to use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air
reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner, not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. Well, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids, all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are 2 things you need to remember. First, ask an adult if you can use the diapers for your experiment. And 2, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. What it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait, that wasn't supposed to go in there. So So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website. This is water. Now, it's ice water. Science. Okay, no, that's not the science part. Here's something you can do at home. Get some ice water and a way to time yourself and stick your hand in the ice water. It's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects the seal and a whale. We don't have blubber, but we are today gonna have some blubber because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this. And you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here, I have 2 bags of blubber, and I've taped all the way around the outside. So I have, a blubber glove. Check it out. So, let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! I can't. Okay. Oh, here we go. Okay, so far. Oh.
The legs are warm. Oh! Blubber suit! Ha ha ha! I am in seals! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah! Blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber, just like I do. Okay, so now, all I have to do is get out. Blubber suit! Oh no! My blubber is leaking. Ah, I've sprung a leak. My blubber. Oh, my precious blubber. No, what a world.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh,
Is that a magnet?
this? No.
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just
It was a good trick, but it's science, not magic.
well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off with my magic. You will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't!
This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Now it is time to talk about an amazing natural polymer. It is hagfish slime? Ugh. Well, hagfish, that's probably just an unfortunate name for the fish. I'm sure the fish itself doesn't. Ugh. Okay, so hagfish makes slime, apparently. When a hagfish is attacked by something that wants to eat it, like a shark or an eel, it secretes a tiny bit of a natural polymer. That's this little white bit right here at the end of this test tube. Now, it doesn't look like much right now, but it reacts with seawater. Watch this. Hagfish slime is very interesting to scientists because you start with just a tiny little bit and add seawater, and suddenly you have a lot of slime. Whoa. This stuff is actually pretty cool. Hagfish slime is a natural polymer. It's made just the same as the other polymers out of long chains of molecules, but it's naturally produced by a living organism. And because it's naturally produced, that means it's biodegradable. Hagfish slime. It's pretty cool after all. Ugh. Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan.
Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So, instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't
all
forget
right?
to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this.
Yep. It helps the pasta to stick together. So as we're rolling, we're rolling, we're rolling. We're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thing
Yeah,
when we're finished with it.
exactly.
This is going to be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta and the little bridge with it.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome. Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be science max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls, bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and yeah, it works the same. Okay, now let's try it with 2 balls. Okay, ready? Wait. And 2 balls, throw them out. And 2 balls on that side. All right, so there you have it. Whoa. Newton's 3rd law. Oh.
Newton's 3rd law. For every action, there is an equal and opposite reaction.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science.
Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science. Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da! Your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. Isn't that amazing? This is gonna be super maxed out sound experiment. This is James, Michaela.
Hey James, how are you?
Thanks for coming, buddy.
Nice to meet you.
So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Awesome. So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes, like your house stereos, and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of thunder,
very
kind
low.
of blah, blah, blah,
Yeah.
where you really feel it, like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science, Mac! Experiments at large! Super sound! High fives.
Yeah.
Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff
Come
up.
on back. Good. Little bit more. Perfect. A cement truck is a perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo. Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that. Whoa, super maxed out! Science! This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
You know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor? Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now we're gonna talk about tension. What's tension? One more than 9-shin. Get it? Because tension and 9, that's, okay, because tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these knots. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science. Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases, like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need. A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers. So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery, and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Haha, a D-cell battery, which is larger and of course larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and haha, it spins. Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this, huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil, I take the copper coil, I need to get, okay, hold on, I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work, but that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement. The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home. Yeah, science! This is our control pumpkin. A control in science means a version you don't experiment on, so you can compare the results of your experiment. So this is what a pumpkin does when dropped with nothing to cushion the fall. Jenna and I really have our work cut out for us because a pumpkin has a lot more mass than an egg, which means it's going to be much harder to stop once it's moving. So now all we have to do is come up with a couple ideas to stop that from happening.
All right, let's do it.
Science. Yeah. Jenna and I are coming up with solutions to the pumpkin drop. We have 3 material science strategies. Strategy 1, polymers. Something is a polymer if it's made of long chains of molecules. Everything in this category is a polymer-based solution. Rubber and elastics are polymers, so I thought, what about a trampoline?
Look to the left a little bit.
My left or your left?
My left. Alrighty, here we go.
And it works great. The pumpkin totally survives until it lands from the bounce. That's it, like it's a success and a failure. Balls are made of polymers like rubber or plastic, so how about a bag of balls? There's the pumpkin. Whoa! I think that worked. Whoa, mostly unscathed.
Almost there, almost there.
Right. Bungee cords are made from elastics, which are a polymer, and it worked, I think. I mean, it stopped it from falling, but never made it to the ground, unless we unhooked it. Technically, it survived better than any other pumpkin, really. Here's another polymer solution. This is cornstarch mud. It's a liquid, but if you hit it, if you impact it, it turns rigid.
Right, so that could protect the pumpkin.
Oh, yeah. And now,
The rest.
we add more cornstarch. Cornstarch mud strategy. But it turns out hardening on impact doesn't cushion the pumpkin much. Yeah, a bit of a problem there.
I don't think this worked.
And every scientist's favorite polymer,
Giant tub of slime!
Where did you get a giant tub of slime?
Episode 6. All right, let's check it out. Little slimy, all awesome.
Now let's recap. This is our control pumpkin, so solutions work if they do better than that. Trampoline? Yes. Then no. Bag of balls? Yes. Bungee cord? I think we need to disqualify that one. Cornstarch mud? Barely. Slime? Yes. Not bad for our first round.
Science!
We've had some good successes with polymers.
Whoa, mostly unscathed.
Almost there, almost there.
Right.
Now it's time to try our foam solution. The first foam we use is fruit netting.
Foam fist bump. Boom. See? That didn't feel like much at all.
Which didn't seem like enough protection.
Pumpkin ball. Pumpkin, actually, pumpkin sphere.
Wrapping the pumpkin in a sphere of foam.
Go pumpkin sphere!
It worked better, but not perfectly.
Uh-oh. It's split right down the middle.
Pumpkin cube!
Phil?
Yeah.
Phil, what is it?
Wrapping the pumpkin in a cube of foam. Better than our control, but you can see the pumpkin crush as it lands.
Oh, no. Phil?
Totally great! How much did it hold together?
Not at all.
I'll give it 3 cubes out of 7.
We need more protection,
Pumpkin helmet.
which leads us to a bike helmet solution. Which worked the best of all so far.
Totally survived!
Oh my goodness!
Yes, I know, this pumpkin's a bit smaller than our control pumpkin, but our big pumpkins wouldn't fit inside helmets, and we figured it was only a fair test if we used a pumpkin the size of your head.
This is why you wear a helmet, Science Maximites. Look at that. Unharmed.
Expanding foam sealant.
And we spray it all the way around the pumpkin.
Expanding foam sealant is special stuff used to insulate gaps and cracks in the walls of your house. It comes out of a can soft, but then expands and hardens to foam.
A full pumpkin completely covered in expanding foam!
Turns out this stuff is made for insulation, not absorbing shock.
Our beautiful foam pumpkin.
I don't think it worked that well.
So now we recap our foam solution. Fruit netting, no. Foam sphere, yes. Foam cube, no. Bike helmets, a big yes. The only perfect pumpkin yet. Expanding foam, no.
So that's it for our foam solution.
I think we should move on to armor now.
Yeah, all right.
We've tried polymers,
Little slimy, all awesome.
we've tried foam.
Uh-oh. It's split right down the middle.
Now it's time to try armor. Anything that protects the pumpkin in a shell of some sort.
This does not look like armor, Jenna. This looks like pumpkin soup.
Our first solution may not seem like armor, but it's a hard shell and the pumpkin floats in the water. When we drop it, the bin explodes, which slows the pumpkin down a lot. The result? Not perfect, but still, remember, it's better than our control.
So compared to the control pumpkin, that did pretty well.
That was pretty good.
Yeah.
I'll give you that.
What is this?
All right, well, we've got a pumpkin covered in knee pads.
Knee pad pumpkin!
Knee pads are armor for your body. So wrapping the pumpkin in knee pads...
Knee pad pumpkin!
Drop it, Phil!
didn't seem to make much of a difference.
Maybe it didn't land on a knee pad. Maybe we just missed. We ended up in between the knee
I
pads.
think that must be it. It's looking a little rough.
But using sports equipment gave me an idea for using an advanced material. It's called sorbethane, and it's used in modern sports equipment. It disperses impact.
See, watch this. Okay, so I've got a hammer, and I hit the pumpkin here, and it goes right into the pumpkin, right? So, take that. Now I hit it again on the sorbethane, and haha, see? Nothing. So I thought maybe this will cushion the impact.
The result? Not bad.
I don't think it dispersed it.
quite well enough. There is a crack coming right from the hole that you made with that hammer.
Okay, so the hole might have structurally weakened the pumpkin a little bit. So the sorbet thing did a pretty good job, actually.
Yeah.
Good thing it is in athletic equipment. That's what it's for.
Carbon fiber is a very modern kind of material.
It's carbon meshed together and then glued down, so it's super strong.
Super strong, and the pumpkin is contained inside. It's like double shields.
Yeah, so can I test how strong this is?
Oh yeah, this is the armor solution, so let's try it out.
Here, better try it.
Whoa!
But when we drop it, we realized there were too many hard surfaces. And not enough cushioning. But the carbon fiber held up really well. Slowing the pumpkin down and cushioning it is the answer, which leads me to my final solution.
I call it the lunar lander. That's what I was doing. I was coming in, right?
Right.
Yeah.
See, I thought we were supposed to be doing armor?
Yes. So this is armor. I know it looks like foam, but you see armor like in a helmet, it's supposed to crumple to protect your head, right? So
Right.
this will also crumple because it's not just foam, there's wood inside. So the wood is supposed to break and then the foam bends and the whole thing is supposed to cushion the impact of the pumpkin. Ooh.
That looked pretty good.
The landing crushed and broke a lot of the arms of the lander, but the braking cushions the impact.
Oh, what do you think?
I think it's good. I think we're good.
Look at that.
And now the awesome recap. Remember, the difference between doing science and just having fun is recording the results. Water bin? Yes. Knee pads? No. Sorbethane? Yes. Carbon fiber? No. Lunar lander? Yes. So, we've had some successes and a lot of failures, and we've learned a lot of things about different materials. And we have one pumpkin left.
There you go, Science Max Experiments at Large, pumpkin drop. Thank you, Jenna.
Thank you, Phil. That was awesome.
And we still have one pumpkin left. Whoa! Whoa, no! I got it! I got it! It's fine, everything's fine.
Fine.
We can
I got this.
Yeah, we
Fine.
can take that up.
Yeah, no, it's
You got it, you got
good.
it. Careful! Oh, well.
Oh, okay, well.
Make that 0 pumpkins left.
I'm here at the Ontario Science Center, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there, right in there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make 2.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these 2 giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That's amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble.
Well, there you go. Giant, smoke-filled bubbles.
Awesome!
Yeah! All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt.
The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance.
But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look.
The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes.
So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that.
This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar, you can use brown or white, I like to use brown, and an adult. Here's why you need an adult. You wanna dissolve 3 cups of sugar into every cup of water, and you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container, and then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big would definitely not be good for my teeth, so yeah. Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry, all of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science.
Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket.
Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone, and 3 hoops for thrusters, and tape them to the bottom.
There you go. The rocket fits on the tube just like that. And when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area and you bring your safety glasses with you, all you need to do to make the stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container, and these magnets are air molecules. Now, I'm gonna put the magnets in pole to pole so they repel each other and wanna stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now, watch what happens when I add more gas molecules. They start to get squeezed together, and if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be science maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out.
I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool and I realized I should have duct taped the pocket because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air. The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result. Now, let's max it out. This is an air compressor. Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready? Just like the small boat, pushing against the air doesn't produce much thrust. Huh, not so great. But now let's put it in the water. Pushing against the water gives me much more thrust because water is more dense than air. Oh. Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me. Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container, and these magnets are air molecules. Now I'm gonna put the magnets in pole to pole so they repel each other and want to stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now watch what happens when I add more gas molecules. They start to get squeezed together. And if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure. If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm in iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. it does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion. An object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. Things' tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh, good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa!
Remember not to try this at home. I am a trained professional.
This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa!
The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood and then we can try changing the bottom. I guess a block of wood isn't the right thing to use though.
Right, yeah. Maybe we could use like a sled.
Yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for us.
Are you sure you want to portal it in?
I'm sure. Just stand back though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is my turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was.
You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yeah.
we'll get some tools.
Yeah.